السلام عليكم شباب. So until everyone joins in a minute or two, I want you to think of that question that we have and write down what you think would be the answer in the chat. And to be specific, what I'm looking for is basically two parameters. What are the two most important parameters when it comes to big scale thermal desalination systems, for example? And I want you to write it down in the chat. Not really. Even the heat input would be a function of Osama has gone to the or has jumped into the production. I mean the outcomes, like how good is the system and what should be the cost of the system. But what I mean here is to produce water. And normally for desalination, for thermal desalination, we rely on heating the water, evaporation, and then condensation. Surface area is a good parameter needed for condensation, and we should have enough surface area to condense the vapor that we have formed. But still, it's not yet the key. Heat transfer rate is not different from the heat input. It's a heat transfer. The amount of sweet water product, again, how can you produce more water? What are the parameters that you need to change in the system so that you can get more water? Say that we are talking about a multi-effect desalination system or a multi-stage desalination system. How can you be able to produce water in every effect or every stage? What do you need to change to get that? From one stage to the other or from one effect to the other. Quantity of water is going to come as a result of condensing the vapor. Actually, I can, just to give you a hint, I would say that it should be something that is related to being able to produce vapor. What are the parameters that are going to make us always able to produce vapor? As you are moving from one effect to the other. Yes, this is what Saleh has written. This is correct. It is basically temperature and pressure. Controlling the temperature and pressure is the key. Actually, pressure is very important in the sense that it is going to, or controlling the pressure is going to result in, or in particular, reducing the pressure as you are moving from one effect or one stage to the next, is the one which is going to result in the generation of more vapor. And the vapor has to be hot at a certain temperature first. And then after that, as the temperature drops and pressure drops, then you are able to generate vapor in the next effect and the next effect and the following one and the following one and so on. So the basic two parameters that most actually all of the desalination systems, thermal desalination systems, are common in terms of being able to produce vapor are the pressure and temperature, even the limitation, so that I cannot increase the temperature to any value that I like because I'm dealing with seawater. So there is a limit, there is a cap on the temperature, otherwise scaling is going to occur. So that issue of being, even when you think of the HDH unit, if I'm able to reduce the pressure in the humidifier at a given temperature, then I can produce more vapor to be carried by the air to condense in the condenser. And that's why, if we recall, when we talked about the HDH part, is that the highest expected GOR and productivity is going to come up from a variable pressure system, where you have low pressure in the humidifier and high pressure in the dehumidifier. So these are the most key elements or parameters or properties that are common in every thermal desalination system. We have not yet talked about the membrane distillation system, which will be starting after we finish the MSF. And the membrane distillation system, basically the motive for the whole process is the difference in vapor pressure between the seawater side and the condensate side. It is the one that drives the vapor to move across the membranes. In multi-effect desalination system, as you are moving from one effect to the next one, the pressure reduces, and that's why the corresponding saturation temperature drops, so that the vapor that's coming from the previous effect, when it condenses, it gives the latent heat, and at a lower pressure and lower saturation temperature, it is going to generate additional amount of vapor and so on. So basically, when you are thinking of a thermal desalination system, these are the two parameters that you need to think of, both temperature and pressure. Reduction of pressure is a very important key, and monitoring the temperature and its variation is another important, because it sets the limit. For the MED system, we said we cannot exceed 70 degrees centigrade, 65 degrees centigrade. What is the reason? Because we are spraying seawater outside the surface of the tubes, and we are concerned about the formation of scale. So to avoid scale, you need to keep the temperature as low as you can, and the lowest possible there is about 65 degrees centigrade to get a decent production. In the MSF, we'll see that the limit, because in MSF, seawater is passing inside the tubes, and we are able to clean the seawater inside the tube so that we can have a little bit of relaxation, and we can go a little bit higher for a temperature of about 90 or 100, or now the current technology is about 120. They are trying hard to reach for 130 by doing proper treatment of the seawater as it passes through the system, so that you can take out the divalent ions or the multivalent ions, for example, talking about the sulfates and the carbonates, trying to clean the water from these, and then you are able to increase the top brine temperature and get more effects or more stages, and hence you can get better productivity of the unit. So this is something that I just want you to keep it in your mind whenever we are talking about thermal desalination systems. Think of temperature and pressure. What we need to consider today is a mode of desalination, which is the single stage flash desalination system. The single stage flash desalination system, we are studying it because This is the intro. It's the introduction to the multi-stage flash desalination system. Worldwide, you don't see a lot of multi-stage desalination systems. But here in the kingdom, as well as in the Gulf area, most of the desalinated water which is being produced is coming out of this technology. As a matter of fact, the whole world is moving into reverse osmosis because they say that reverse osmosis is cheaper, it's easier, it's lowest in terms of power consumption. To some extent, this is not accurate because, for example, that has been built, or this has been an idea that has been capped upon the high energy consumption related to the single stage flash. The goal of a single stage flash system is by most a value of 9.5 to 10. It does not exceed that value. But in the MED, we could see that the GOR is, or the PR, performance ratio, is a function of the number of effects. So if I have proper treatment of the seawater so that I can increase the top brine temperature to something like 90, and if I connect it to a system that can decrease the low temperature side of the plant, then I can easily accommodate something between 16 to 20 effects, and then the GOR becomes 20. And this is a value that is very much comparable to what we can get to the RO, and even it's better. The reliability of the systems is better when we come to the thermal systems. Multi-stage flash desalination system has been built to live 25 years as a plant lifetime. In Khobar and in Jubail, we have plants that are operating for 38 years, and they are still operating with the same performance as if they were in day number one. Definitely, there is some sort of accumulated knowledge between the engineers and technicians of how to maintain these systems. The plant factor, which is what are the times of shutdown all over the year for maintenance. So when we talk about the number of hours in the whole years these plants are operating, it's something which is 95% or more. So you are talking about a very reliable system in producing sweet water. The only drawback when it comes as the comparison between MED and MSF is that MED you can go for performance ratios easily, you can get 15 and 16, whereas the ceiling for an MSF system is 9.5 to 10, which again is not true, because this is because there has not been some sort of breakthroughs or new ideas that would be applied to the single stage flash that can bring it to a higher value of the PR, performance ratio, or the GOR, gain output ratio. Maybe one trial of this is something that we have done. I had one student who was doing his master, actually happens to be the director for training in the SWCC DTRI, which is the Research Institute, or the SWCC plants in Jubail. He was doing his master maybe 1.5 years ago, and his work was basically related to single stage flash desalination system. And the question that we have started to talk about at the beginning was, is there a way that we can have improvement in the MSF system so that we can break that ceiling of 9.5 to 10 as a PR for these units? And what we did, we took one of the desalination plants in Jubail, which is basically was Jubail 2, as far as I recall. And we started to think of what we can do to have the system in performance improved. At the end of his thesis, he showed that he can get like something between 50 to 60% improvement in the performance. So we could reach for a value of the PR, which is somewhere between 14 and 15. So that answers that kind of important question. Is there a limit? No, the answer is not. Just come up with new ideas, apply it, and then you'll be surprised by the results that you can get. The point now for us is, are we able to persuade or convince the manufacturers to adopt the idea that we had in order to have better productivity? The answer might not be yes, or it's not an easy yes. Why? Because there has been a lot of investment in the membrane business, and this investment has to return in a certain kind of applications and addition, and of course profits. So as if the desalination companies are driving the whole world into, I'm talking about the manufacturers, into RO systems, although it might not be, as of today, the best solution for every problem related to desalination. Why I'm saying that? Because in some places, in some cases, they are definitely better. If I'm going to build, or if I need to think of a desalination system for brackish water, definitely without saying it's the RO. Why? Because the brackish water has low salinity, relatively, I'm talking about to seawater, something in the order of 10,000 ppm. And definitely the kind of power needed to operate the unit is much, much small compared to these. So it's the best option. When it comes to the seawater quality of the Atlantic Ocean or the Pacific Ocean or the Mediterranean, RO is a very good competitor because the kind of energy needed for operation there is small, because the salinity is about 28,000 ppm. But when it comes to a salinity of 45,000 ppm and other problems related to the water, like the turbidity of the water, the quality of the water, and some of the associated problems that are located in the Gulf, as well as the southern part of the Red Sea, you'll find that over there, the specific power output, which is coming from an RO system, for example, is not 2.5 as what you can see in the Atlantic Ocean, but it can even reach for a value of 8. For the MED, it's already 4, and it is irrelevant. It's not related to the quality of water. So that brings a question here. Another issue is the productivity. If you are in need of producing large scale of desalination, then you would think of thermal desalination systems. If you are needing power, then it becomes more relevant to have a system to produce power, like a Rankine cycle thermal power plant, and to produce and desalination water to take a line of steam from the turbine and operate a desalination plant. But if you are living in some place in the States or Europe and you have a river, so that if you have a river, then you do not really need to have a thermal desalination system, because the river, you can put turbines, the turbines can provide electricity. And if you have electricity, then you can run an RO system. One more thing, if you need to build a medium scale unit, then RO is the best, because the economics for a medium scale or a small scale unit are in favor for the RO. For the thermal desalination systems of large scale, like MED and MSF, to be built, like the one in Jubail, we have the MSF, the MED is producing 800,000 cubic meters per day. Ras Al Khair is producing more than 1 million cubic meter per day. So when you come to about this very large production, then these units of the MED becomes more competitive. I would not say the MSF with the current technology, but with an improvement in the technology, that's something that can be like a good competitor to them. I did not mention the idea that we have done with the MSF system, which is basically was to connect a thermal vapor compression unit But that, I mean, it has some more details that needs to be done, but was basically the idea. Attach a TVC and select the best location where the TVC is going to be placed, and then do some adjustments in terms of flow rates, and then you can get some sort of a better productivity. This was some sort of a long introduction, but by the introduction, I would mean to say that when we are talking about research, the RE that we have at the beginning of the word, it seems that again and again. So you search again and you search again and you search again, and that's why it's called research. And sometimes you can come revisit some of the technologies that people started to abandon. And then you can find out an opportunity there, and you can bring up some new ideas that are comparable to what's available. The link that we have in the unit or in the page that we have here is taking us basically to Sidem, which is one of the producers of desalination systems. And the producers of the desalination systems are basically some major companies, like in Korea, they have Doosan. In Japan, they have Sasakura. In France, they have Sidem or Veolia, and they are all producing thermal desalination systems. This is what you have in MSF. I took this from the site, that's why I put the link over there. The idea behind a thermal desalination multi-stage flash system is, you can see it here. Seawater is entering into the tube bundle. The tube bundle is receiving seawater at normal seawater temperature, about 30 degrees centigrade or so. It is entering here, and the liquid here is being preheated. It is preheated by the vapor which is coming from below. So the vapor preheats the liquid. So have preheating here, and preheating here. And this why this section of the plant is called heat recovery section, because we are recovering some of the energy that we spent in the heat exchanger here, which is called the brine heater. You have seawater coming here at a temperature of, say, 30. Here it's 35, 40, 45. So instead of bringing seawater at 30 to enter the brine heater, we have brought temperature of the water up to 45, and then it will enter here. So have basically reduced the quantity of steam which is needed. Steam here is coming from the power plant, and it is going to heat the seawater from T1, which is, say, 45, to the top brine temperature, which is 90, or 10, or 10 and 12 as of the current technology, or 10 and 20, which is the technology that they are working into. So this is what we call the highest temperature of seawater here. This is liquid seawater. And this is what we refer to as the top brine temperature, TBT. Water at this top brine temperature is going to enter to the first effect. This is basically at a pressure higher than the atmospheric pressure. It will enter to the stage which is at atmospheric pressure, and due to the pressure difference, flashing will occur. The vapor that will flash here is going to condense on the surface of the tubes. It will preheat the water coming in, and then it will condense into sweet water, which is collected in a sweet water tray. The part that will not evaporate is going to go to the next effect, where this kind of black vertical line here, or this line here, is showing that we are undergoing a reduction in pressure from one stage to the other. So this stage is lower in pressure compared to the previous one. And then flashing will occur. Vapor is going to condense here to give sweet water, preheat the feed, and the quantity that will not evaporate is going to be transmitted to the next stage, which is at a lower temperature, and so on. And then you are collecting that distillate from each one of the stages, and this is the distillate collection. Brine, which is leaving here, normally you have the brine leaving at a temperature of 40 degrees centigrade, and this is going to be rejected back again to the sea. And you get rid of non-condensable gases by having air extraction, so that you can just have a way to extract the non-condensable gases out. And the steam, after condensing here, it's going to go back again to the power plant. One more thing that can be done is that you can connect the last stage with um, uh, a vacuum system so that you maintain the whole unit at a lower pressure so that you guarantee there's a pressure reduction as you are moving from one stage to the other. The system that we see in front of us here is what we call the once-through system. Why? Because seawater comes in, preheated, then heated to the highest top brine temperature, and after that it will flash and flash and flash and then rejected back again to the sea. What's the problem with this system? They thought of this system as the beginning, but they found out that in order for the seawater to come in, there is a lot of chemicals that are added into it as anti-scalant, anti-foulant, anti-foaming. So something to improve the quality of the seawater as it comes in and reduce the issue of scaling. And you are here basically throwing to the atmosphere or throwing to the sea again, treated water with chemicals. So the chemicals that you spend here, these chemicals will not evaporate, they remain in the water. Maybe part of it will leave as part of the non-condensable gases like the carbonates or so, as it comes to the seawater. So some vapors would be leaving in, but most of the chemicals that you have paid for here, you have invested in, are going to be thrown away. This is a loss. That's why they came up with a unit or with the idea of brine recirculation. So that this is the steam generator or the brine heater, and this is the brine heater, or the main heat exchanger for the unit that heats the seawater to the top brine temperature. This is the heat recovery section, and they added more effects as what they call heat rejection section. What is the heat rejection section made of? We take the brine leaving here, and we add 2 more or 3 more stages here. We don't throw all the brine out, but instead, we have the seawater coming, we preheat the seawater to a certain temperature, which is equal to the temperature in the last stage here. And then we bring that seawater again, or this amount of seawater, we throw away part of it, and the rest is going to be added to the water, that we take the water here and we re-inject it back again to our effects. And then we throw away a very little quantity of high salinity water. Why are we doing that? Number one, this water which has reached here, which is treated, is not thrown away. But we dilute it, we reduce its salinity by adding some fresh water at the same temperature. But this should be at the same temperature. So that's why we needed to heat the water, and we heated it here in these 2 effects. We are producing some more desalinated water here. That's another benefit. And we are recirculating the brine. That's why it's called the brine recirculation. We are recirculating it again to flow into the heat recovery section. So we saved the chemicals by not throwing that brine away, but taking the brine and recirculating it back. This is one benefit. The second benefit, we are recirculating the brine at this temperature, the 40 degrees centigrade. So when it comes here at 40, it might leave here at about 65. Actually, in actual cases, it might leave closer to 80 or 90 degrees centigrade. So have you reduced the quantity of energy needed here to reach for the top brine temperature? What is the penalty that we have to pay? Is you see the pumps here are given in circles. Look at the size of the circles and look at the size of this circle. So we need a lot of energy for the brine recycling pump to operate. And this is why the multi-stage flash brine recirculation system is demanding in terms of power. And this is why they say, if you are going to compare this with an RO system, the RO system maybe needs this amount of power and that's it. But here we need amount of power to run the pumps and heat for the system as well. So that makes it demanding in terms of the energy. And actually, yes, as of the technology that we see in front of us, you have to produce mechanical power in terms of the pumps, and you have to add thermal powers in terms of the heating system. Now, this is an overview of the multi-stage flash desalination system. But what we need to focus in now is the single stage unit. The picture that you see here is Al-Khobar 2 multi-stage flash desalination system. Each one of these is an MSF system. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 MSF units. Each one of these is made up of a certain number of stages. As a matter of fact, we have 19 stages here. 16 as heat recovery section and 3 as heat rejection section. To remind you, this is the heat recovery section and this is the heat rejection section. And we have here 1, 2, 3, 4, 5 Rankine cycle units. They are producing electricity as well as water. Each one of these units is producing, or each one of these MSF units is producing 26,700 cubic meter per day. When you are talking about 10 units, then the productivity of this part of Al-Khobar 2 is 267,000 cubic meter daily. And it's not the only one here, but we have Al-Khobar 1 and there is also Al-Khobar 3. So these are some of the desalination parts or desalination systems of MSF that are operating. Definitely it's on the sea because it takes the seawater in and then rejects the brine down. What we need to do now is getting into the analysis and the performance evaluation of multi-stage desalination systems. In order to do that, we're going to start with a single stage as usual. You can hardly find a single stage unit, but you can always find a multi-stage desalination unit. As I said, in the Gulf area here, there's a lot of these units. Some countries in the Mediterranean, in the North Africa have, Libya, for example, has multi-stage flash desalination systems, and they are still up and running. Now let's look into the single stage desalination system and look at the performance measures or how we are looking at the performance of these systems. This is a stage. In the stage, there is seawater coming inside the tubes. There is brine pool at the bottom, and the brine pool basically is having the brine coming in from a higher pressure area. Flashing will occur, the vapor will go up, the vapor will condense in the outside surface of the tubes, and it will be collected here in the distillate tray. So this is a sample of one stage. This is what you see in a single stage system, and actually, the figure here is telling us a lot. This is the brine heater, the one which is shaded in blue. And this is the stage. What happens? Seawater is coming here at a temperature of 30 degrees centigrade, salinity of about 40,000 ppm, a flow rate of about 115 kilogram per second. This is tremendous amount of water coming in. It will get here. As it will be preheated, vapor is going to condense. The big quantity here is just to make sure that all the vapor which is being rising here by flashing is condensed. And when it condenses, this whole quantity is going to help producing only 1 kilogram per second of water. This water is going to be heated from 30 to 35. Normally, it's about 5 degrees per stage. So 35 here, you throw away the cooling water that you have here and you only pass the feed so that you heat the feed from this temperature of 35 to a top temperature here of about 90. And the quantity that you are heating here is only about 11.5 kilogram per second. This 11.5 kilogram per second is going to enter into the stage at the bottom. A part of it will flash. The part will flash is only 1 kilogram per second. And we are throwing away the rest, which is 10.5 kilogram per second to the sea. The 1 kilogram per second that will rise here as vapor is going to condense and will collect it as sweet water or as a product. Salinity has increased due to this process from 42,000 up to 46,000 approximately. So this is basically what will happen in the single stage system. Any questions? Is it clear, يا شباب?
Yes, Doctor.
Now let's look at the assumptions. Again, distillate production is free of salt. CP is treated as constant. We are considering a constant overall heat transfer coefficient. We are neglecting, as usual, subcooling or superheating the steam. Actually, steam that enters here, we assume that the steam comes as saturated vapor and leaves as saturated liquid. That makes it easy for the analysis. And the parameters that we are looking for, as usual, for any thermal desalination system is the performance ratio, the heat transfer area, the quantity of cooling water which is needed for the system. And definitely what we call the recovery ratio, which is how much distillate water compared to the steam, to the seawater which is coming in. Some typical values are given here. T note, which is the top brine temperature, is 90. In this case, actually, currently we can reach for 120. What's the difference between having at 90 and 120? The difference is the flashing range. If the seawater temperature, if the top temperature is 90, and the temperature of the water that we throw away is 40, then the difference is 90 over minus 40 is about 50. If the delta T per stage is 5, then we can have 5 stages. But if this value, we can have 10 stages. But if this value is 120, so 120 minus 40 is 80. So that we can have like 16 stages. And this is the key. Increasing the number of stages is one key parameter to increase the productivity. This is not like the MED. The MED increasing one effect means increasing the PR by 1. This is not in the MSF, because in the MED, we are generating vapor by the used vapor, like vapor which is formed in one effect goes to the second effect as a source of heat. This is not the mode here. The mode here is that you have heated the water to top brine temperature, and then you have flashing and flashing and flashing and flashing and so on. You are making use of the vapor only to condense for preheating the feed. So there's no regeneration of vapor as what happens in the MED. 40 degrees centigrade is the rejected brine temperature. Steam temperature is higher than the top brine temperature by 10. And this is just for the size effect of the process, for the size of the brine heater. Cooling water is coming at 30 degrees centigrade. Thermodynamic losses in every effect is 2 degrees centigrade. This is due to the losses due to friction, losses due to boiling point elevation, and so on. The terminal temperature difference in the cold side, which is basically the difference between vapor temperature, which is rising, and the outlet seawater temperature from the effect. This is what we call terminal temperature difference in the cold side. 3 degrees centigrade, and this is the intake salinity and maximum allowable salinity as it leaves the system. This temperature profile is extremely important. I'm saying it now that every one of you should be able to sketch this temperature profile. This is what happens in the brine heater, and this is what happens in the flashing stage. In the brine heater, you have steam coming from the power plant. It's coming as saturated vapor, leaves as saturated liquid. So it's a condensation of the steam at constant temperature. It gives off its latent heat of condensation for the seawater to be heated from T1 to T0, which is the top brine temperature. This difference between the steam temperature and the top brine temperature is what we call terminal temperature difference in the hot side. The word terminal temperature difference means if you have a heat exchanger, at the exit of the heat exchanger, you have two streams going out. What is the difference in temperature between them? We call it terminal temperature difference. And then for the stage, the top brine temperature the seawater at the highest temperature that leaves the brine heater is going to enter to the stage where it's going to be reduced in temperature due to flashing from T naught to Tn or Tb. This is the brine rejected temperature. This is the temperature of the brine which is going to be thrown away to the sea. And vapor is going to form here by flashing. Vapor is less than the T brine by the delta T loss, which is, according to this assumptions, it's about 2 degrees centigrade. It is this temperature. And accordingly, it includes the boiling point elevation. So the vapor temperature, if this temperature is about 40, then this is going to be 38. So you have vapor at 38, which is condensing at constant temperature, and we are going to make use of it to preheat the seawater from T cooling water into T1. So the highest temperature, which is leaving that seawater stream, is T1. So the difference between the vapor temperature and T1 is what we call terminal temperature difference in the cold side. This is the one which is being listed here, TTD, terminal temperature difference in the cold side. And that's the one that I mean here. This sketch that you see in front of you is the key for solving most of the problems related to the single effect flash system or single stage flash system. These are the basic equations that we are using. The mass balance, the feed which is coming is part of it will be converted into sweet water. The rest is going to be rejected brine. And the feed here is coming at the inlet here to the brine heater. This is the feed entering here. It will be heated to the highest temperature, and that feed is going to enter to the effect. Part of it will leave as vapor that will condense into MD, and the rest will be leaving as brine, and which is MB to be thrown away back to the sea. So basically, m dot feed is m dot brine plus MD. The salt balance equation, m dot feed into x feed is m dot brine x brine. The distillate is free of salts, so that's why there's no other parameter. There's no xd, for example, it's equal to 0. Then, inside the heat exchanger, which is the brine heater, we have steam condensing. So m dot steam into HFG is the energy which is given for the brine heater. We can call it Q brine heater, for example. Which is m dot steam into HFG of steam. And this is going to be used to preheat or to heat the feed, m dot feed, from T1 to T naught, which is top brine temperature. So again here, T naught we refer to as TBT, and the TBT stands for top brine temperature. Then in the effect, in the stage, there is vapor which is formed. This vapor is coming by flashing. So m dot d HFG, the energy needed for vapor flashing, is coming from the reduction of temperature of the feed. The feed has cooled down from the top brine temperature to TB. So this is what happens as flashing occurs. The vapor which is going to be rising up, it will be utilized to preheat the water coming, which is the feed plus the cooling water flow rates. It will heat it up from 2 cooling water to T1. So the energy balance, which is in the stage, is given by this. And it simply says that there is seawater coming after leaving the brine heater at the top brine temperature. It will cool down from T naught to TB, which is a rejected brine temperature. In order to do that, or while doing that, some vapor will flash, which is m dot distillate into HFG, and this vapor will condense. As it condenses, it is going to preheat the feed and cooling water coming from T cooling water to T1. This is the heat recovery part that we have in the unit. Then, in the brine heater again, the QB is going to equal to the overall heat transfer coefficient into the area, into the log mean temperature difference, where the log mean temperature difference again is T naught minus T1 over ln T minus T1 by Ts T minus T naught. In the heat recovery section, there is vapor that will condense to preheat the feed from T cooling water to T1. So Q of the stage here, or Q for the condensation process, is is m dot distillate HFG. It's equal to the overall heat transfer coefficient for the condensation tubes, area of the condensation tubes into the log mean temperature difference of the condensation tubes. And the log mean temperature difference is being calculated here. You have vapor, which is bringing the seawater from T cooling water to T1. TV minus T1, this quantity is what we refer to as the terminal temperature difference in the cold side. So basically, these are the equations that we need for the analysis of the unit. The performance ratio is basically m dot distillate over m dot steam. And as a matter of fact, this is all what we need. What you see here is basically some sort of algebraic manipulation. Thinking of that, we can reach for a closed form equation for the PR. Like what we did that also for the single effect evaporation. And I told you that you don't really have to look at these equations or memorize them, or look at them to memorize. You can just look at them to see that, yes, we're able to produce a PR in the system in terms of parameters that could be available. If you know those temperatures, the m dot FCP are going to cancel out together so that you have T naught minus TB over T naught minus T1 with HFG over HFG vapor. So as if I'm saying that, yes, we can obtain the PR in the form of closed form solution. That's it. But in order to solve the problem, I don't want you to memorize these, but going through this analysis is the best so that you can just move step by step to solve the problem. And that, again, you are trying here. This is basically what you'll see in the book. He's trying to come up with like a closed form solution for the performance ratio, as you can see it here. HFG into delta Ts over delta T stage, delta T loss, terminal temperature difference, and the ratio between HFG vapor and HFG of the steam. So these equations are redundant equations. They are repeated equation only due to the algebraic management, which is for the equation. The walls, the ceilings, and the partitions of every stage are basically made of carbon steel, which is covered by stainless steel or epoxy cladding. You are talking about seawater. Seawater is corrosive, so that you need to protect your material, and protection is by, you cannot build it all from stainless steel, it will be too expensive. So you build your units of the flashing walls, the flashing chamber. You build it from carbon steel, and then you cover it with stainless steel or epoxy coating. The tubes are made of basically alloys. Copper nickel alloys would be there. Although the high temperature side of the unit, you better use titanium. It's too expensive, yes, but sometimes this is something that you have to do for the high temperature side of your system, just to avoid the issue of corrosion of the tubes or scaling that would occur. And the tubes are basically copper nickel. You have copper nickel 70-30 and copper nickel 90-10. So the point here is more nickel will be needed for the high temperature, greater than 80, whereas less nickel can be allowed for the low temperature, which means that economically, you are not going to use the same kind of tubes for every stage, but the high temperature stages, you can use titanium or copper nickel 90-10, and the lower temperature stages, you can go for copper nickel 70-30. Why copper? Basically, because the thermal conductivity is high, and then you have better heat transfer between steam and the seawater, or vapor and the seawater. Titanium provides the highest erosion resistance, although titanium having a lower thermal conductivity, but you can use tubes that are very thin. Accordingly, the thermal conductivity of these units is not going to be like a burden on the heat transfer rate. Aluminum bronze is a cheaper material, but its copper contents has dissolves with the seawater. It's a problem with seawater and copper anyway, that it eats up the copper, so that you have to protect it with this sort of alloys that we're talking about. Titanium, although expensive, but for high temperature side, it's the best choice for operating the unit. So that was just kind of the introduction that we have for operating the single stage flash desalination system. Let's now consider an example. And I'm going to stop sharing this. And I'm going to share a file that has an example header, and then we can solve that example together. Oh, sorry, I'll just close this one. And I'm going to share with you this, I think it was a Word file. Yes, this was basically something that it has a summary of what we have just mentioned now. And then at the end, it is having some sort of an example. If you have a pencil and a piece of paper, you can copy this value, because we are going to need them while we are just bringing a blank page to solve. We are talking about a top brine temperature of 90, rejected brine temperature of 40, steam temperature of the top brine temperature plus 10, so it's about 100 degrees centigrade. Intake seawater temperature is 30 degrees centigrade. Thermodynamic losses are delta T loss 2 degrees centigrade. Terminal temperature difference is 3 degrees centigrade. Intake seawater salinity is 42,000 ppm. Maximum allowable, that does not mean that we have it. I'm going to take this out so that it will not confuse us. But the value of T of brine salinity is not given in this example. But what is given is the overall heat transfer coefficient in the hot side is 2.5 kilowatt per meter square Kelvin. And the overall heat transfer coefficient in the cold side is 2 kilowatt per meter square Kelvin or centigrade. So this is basically the kind of information that we have in the problem. What we need is the PR, areas, and cooling water. You will notice here that brine salinity is not provided and the feed flow rate is not provided. So I hope you have taken a note of these parameters that we have here in front of us. And let's first look at this. What is being given to us? We are given T naught here, which is 100 degrees centigrade. We are given the value, there is T steam, which is 100 degrees centigrade. T naught, which is 90 degrees centigrade. T naught is 90. TB is 40 degrees centigrade. T cooling water, which is 30 degrees centigrade. But we don't have the value of T1. And we don't have the value of T vapor. So this is something that we are going to bring from this figure. The delta T loss has been specified to be 2 degrees centigrade. So if TB is 40, what's the value of TV?
38.
Mean معايا 38, okay. And if this is 38 and the terminal temperature difference is 3, so what's the value of T1?
35.
Yes, so this is why I said that you need to have or to know how to sketch this figure, because now from the figure, without having to go any calculations, we could come up with the unknowns TV and T1. So in addition to what we have written earlier, we can also write that TV has been calculated to be 38 and T1 has been calculated to be 35 degrees centigrade. So this is something just beginning to say. Now I'm going to stop sharing this and I'm going to start like an open screen here through the whiteboard. And we need to apply the balances that we have considered for the calculation of the needed parameters. For instance, if I started writing down the mass balance equations in which we can say that m dot feed is equal to m dot distillate plus m dot brine. This is what we used to write earlier, and that m dot feed into x feed is m dot brine into x brine. What do we know out of these? We know m dot distillate and we know x feed, but we don't know m dot brine, m dot feed, or x brine. So we cannot at the moment solve these two equations together. There's something still missing here. Let's look at a sketch of the system. So we have a brine heater and we have a stage. So having these, we have basically kind of seawater coming in here. It will pass by this tubes. It's coming at T cooling water. And here we have m dot feed and m dot cooling water. It will reach here to a temperature of T1. This T1 is going to enter here into this brine heater and it will leave as T naught. T naught will enter here and it will leave as TB. What will happen inside is that vapor is going to form. It will rise up. And here we have distillate tray, which is collecting the distillate. And there is some sort of a demister here, so that the vapor will pass by the demister so that no droplets are going to form here. It will condense here, and then it will be collected as distillate water here. And this is basically the kind of brine pool that we have inside. In order to do that, we're going to need steam coming from the power plant, which is going to condense here. So this is coming at T steam, leaving at the same temperature, and it will convert only from Hg to Hf, and the quantity is m dot steam. Now, the kind of information that we have here basically is the energy balance in the stage would say that m dot distillate into Hfg of the vapor. Do we know this? M dot is 1 kilogram per second, and we know the vapor temperature, so Hfg of the vapor can be obtained. If you are going to operate something like ES, it will tell you that this value is 2411 kilojoule per kilogram. And this is in balance with the quantity which is leaving here is basically m dot feed. So m dot feed into Cp into T naught minus Tb. What do I know here? The left-hand side, I know MD is 1 kilogram per second, HFG is 2411. And the right-hand side, I know the value of Cp, say it's 4.2, T naught is 90, and TB is 40. So the only unknown here is m dot feed. You solve for m dot feed in this case, and the value of m dot feed that you are going to bring will be 11.48 kilogram per second. Wow. So you have introduced 11.48 kilogram per second to bring you only 1 kilogram per second as product or distillate. So this is m dot feed. Now I know the value of m dot feed. So the only unknown here in this equation is XB. So I can calculate the salinity here, which is going to be about 46,000 ppm. Now we know the value of m dot feed. So if you are going to go to the brine heater, what happens in the brine heater? We have steam coming, it will condense, and it will condense to heat the seawater, the feed water, from T node, from T1 to T node. M dot steam is not known. HFG of steam, you can obtain it from the tables or from ES as 2256 kilojoules per kilogram. The feed we know it now. We have obtained the feed. The CP is known. T node is 90 and T1 is 35. So the only unknown here becomes m dot steam. You can calculate the steam mass flow rate here. Do I have the value of the steam mass flow rate? Let me check. M dot steam is going to be 1.175. Kilogram per second. Now I'm in a position to calculate the PR, m dot distillate over m dot steam, and the value is 0.851. Remember this. Do you remember what was the PR when we solved an example for the single effect evaporation? Anybody remembers that?
Much lower than
Single effect evaporation.
around 1.
The value was 0.97 or so. So the single effect evaporation in that sense is operating better than the MSF. This is interesting. So keep that in mind.
But how come, Doctor? But the production here is more than the single effect evaporation.
Again, what you mentioned? What did you say?
How come the performance is higher in the single effect evaporation and the production is more here with the...
No, the production in the single effect evaporation, and the production is 1 kilogram per second anyway, here or there. But here we needed much more water to come in. The productivity for both of them is 1 kilogram per second. But here we used more steam compared to the previous one. If you remember the previous one, we used to have m dot distillate is 1 kilogram per second. So the feed is 2.5 kilogram per second. Right here, we have 1 kilogram per second and the feed is about 11.5 kilogram per second. So it's more demanding in terms of energy compared to the MED. And that's why in the MED, you have normally higher GOR or higher performance ratio compared to the MSF. Is this point clear?
Yes.
Okay. Saleh, you have a question?
Yes, Doctor. In energy balance, we consider only M dot F. Is this mean that the M cold water is rejected?
Yes, actually what happens here is whatever is coming here is basically m dot feed plus m dot cooling water. Before you enter to the brine heater, you get rid of m dot cooling water. Why should we heat it? If you put it in here, the temperature will not It would never be 90, it will be much less. So that you don't need to heat all of this quantity. It will be a lot of energy needed for nothing. Only what you need to heat here is m dot f. So we get rid of m dot cooling water away to the sea, and we only pass the m dot f here inside the brine heater. Is it clear now?
Yes.
Okay. Now, having calculated the PR, we can make a simple energy balance to calculate the cooling water flow rate in the stage. So this would be basically the kind of energy that we have calculated, which is m dot distillate into HFG of the vapor, which is going to condense here outside the surface of these tubes. This is going to bring the flow in, which is m dot feed plus m dot cooling water. It will heat it up from T cooling water to T1. I have this 1 kilogram per second. I have this quantity. I calculated m dot feed already. CP is known. T1 is known, 35. T cooling water is 30. So I can calculate the m dot cooling water, which is needed here. And the m dot cooling water can be calculated to be, let me see if I have this value here with me. Yeah, it's about 103 kilogram per second, about this value. Now we have calculated the PR, we have calculated the m dot cooling water, so that the specific m dot cooling water, which is m dot cooling water over m dot distillate, is about 103. What's needed then is areas. So to calculate the area, maybe I can calculate one of them and I leave the other one to you. So I leave the steam, the brine heater for you, and I will go through the calculations of the area needed for the effect, which is basically, or for the stage, which is basically the heat transfer area needed for that tube bundle. We have a tube bundle here that we need to know what is the surface area for this. Now, this is basically a case where I have vapor. This vapor is condensing, and to condense, it needs to, or it will preheat the feed. So we have T versus X. This is T vapor. In our case, it is 38 degrees centigrade, and it's heating the m dot cooling water plus m dot feed from T cooling water to T1, so that delta T1 is T vapor minus T cooling water. Delta T2 is T vapor minus T1. And to remind you, this is what we refer to as terminal temperature difference in the cold side. So the log mean temperature difference is basically delta T1 minus delta T2 divided by the natural logarithm of the ratio. So then log mean temperature difference for this case is going to be 5.1 degrees centigrade. Q in the cold side, which is m dot distillate into HFG of the vapor, is going to be in balance with the overall heat transfer coefficient. It is given as 2 area into the log mean temperature difference of the cold side. And here we know Q already because we know these quantities. U is given, we calculated log mean temperature difference, so that the area here is going to be calculated as 236.5 meters square. Then I'm going to leave it to you as an exercise to calculate what would be the heat transfer area for the brine heater. If you remember, the brine heater is having energy N, so Q for the brine heater is nothing but m dot steam into HFG of steam. And this is going to be in balance with the overall heat transfer coefficient in the brine heater, 2.5, area in the brine heater, and the log mean temperature difference in the brine heater. And for the brine heater, again, it has a similar figure to this, such that you have basically steam, and you are heating from T1, you are heating the feed from T1 to T node. So delta T1 is Ts minus T1, delta T2 is Ts minus T node, which is the thermal temperature difference in the hot side. You can calculate the log mean temperature difference. Overall heat transfer coefficient is given, Q is known. So from here you can calculate what would be the area of the brine heater. And when you do that, just for you to check your values, this area is going to be 36.1 meters square. The only thing to consider at the end after doing all that is calculations of the specific heat transfer area. And in this case, the specific heat transfer area is going to be calculated as area of the brine heater plus area of the condenser tubes that we calculated here, both of these divided by m dot distance. So now this is the kind of analysis which is normally done with a single stage flash system. We started the problem not knowing a couple of temperatures that we could obtain from that temperature profile by just plotting the temperature profile. And that's why I want you to be able to draw it on your own. And then we did not have the rejected brine salinity. We did not have the feed flow rate. So we have to make an energy balance for the stage so that the kind of vapor that has formed here is formed due to flashing. So m dot distillate into HFG, which is the energy needed for making the vapor, is in balance with the cooling here, which is m dot feed Cp T node minus Tb. And through this, we could calculate the value of m dot feed. Then we went to the mass balance to to calculate the salinity of the rejected brine. After that, we did only heat transfer equations. Our thermodynamic balance, a thermodynamic balance here for the preheating seawater, which is preheated by the vapor, so we can calculate how much is the cooling water needed. And then area calculations for that tube bundle here and area calculations for the brine heater as well. So that is typically what you would do in a single stage flash desalination system. Now, today a homework is going to be given for the MED, and we need to set a time for a quiz for the MED. And I think that would be not next Wednesday, maybe next Wednesday is going to be, or Thursday will be due date for the homework, and the following Monday will be our quiz for the MED system, inshallah. Any questions?
Doctor, if you could make it as the deadline as the previous homework, like in the weekend, so we can work on it on the weekend.
Fine. So you can work on the weekend, and maybe I can put it as Saturday will be the due date, Saturday night, for example, so that on Sunday I can post the solution before the quiz, so that you have enough time with the solution then.
Great, thank you.
And still, Hadi, I have not heard from you and your group. Hadi is not here now, but Abbas El Yahya is here. I have not heard from you about your project. So please today send me a message telling me what is the project that you have selected and what's your plan. You are late in this. So we'll see you next time inshallah يا شباب. السلام عليكم. تفضل يا صالح, you have a question?
Yes, the name of MSOT, can you detail or explain more?
What is it again?
OT, what is referred to what?
OT, it stands for once through. We'll be talking about once through in details, by the way, next time. So there is once through OT and there is BR, brine recirculation. And we are going to deal with each one of these in details in the coming classes, bismillah.
Thank you.
All right, did I answer your question, ya Salah?
Yes, one more question.
Yes, go ahead.
The best tube for heat transfer is copper nickel.
The best tubes for heat transfer is copper nickel, yes, because copper has the highest thermal conductivity, but there's a problem with copper when it comes to seawater. That's why they just put the alloy of copper and nickel together. They increase the quantity of nickel at high temperatures, or they maybe go for another material with low thermal conductivity, but they use less thickness of the tubes, which is the titanium. But it comes as a good solution for high temperature side. So that titanium has a very good resistance to erosion and it does not corrode, and that's why it's used at high temperatures.
Well, when the pipe is attached to the heater or the source of heat directly, which is the best, titanium or copper nickel?
When it comes to higher temperature, titanium is the best. At higher temperature applications, titanium is the best, although it's much more expensive, but they have to do it just for longer life.
Thank you.
You're welcome. اوكي شباب, بشوفكم المرة الجاية ان شاء الله على خير بإذن الله.